one of the outreach coordinators here at ICTP, and I will present in Portuguese our next activities that will happen here in the next days. Então, o ICTP-Safer é o Instituto Sul-Americano para Pesquisa Fundamental e a gente faz muitas atividades de divulgação científica para diferentes públicos, professores, estudantes e atividades voltadas para o público geral. A gente tem três eventos principais que ocorrem para o público geral. Eu vou convidar vocês para os próximos. Então, a gente tem para o público geral uma atividade que acontece no cinema, que se chama Ciência no Cinema, em que uma vez por mês a gente projeta um filme no Cine Belas Artes, na região da Paulista, e convida cientistas para conversarem sobre a ciência no filme. O próximo filme vai ser no dia 26 de novembro, que é uma quarta-feira, que a professora Ilana Werner vai conversar sobre esse filme o dia depois de amanhã. A gente escolheu esse filme porque, em novembro, todos vocês devem estar sabendo que acontece a COP30 aqui no Brasil. A Ilana é uma pesquisadora das mudanças climáticas e da oceanografia física, então ela vai falar também sobre a COP30, enfim, sobre o filme. Eu acho que vai ser um evento bastante importante para quem puder participar. A gente tem outro evento, que é o Papos de Física, que acontece na Cervejaria Nacional. O próximo vai ser dia 27 de novembro, com o professor Alexandre, aqui do IFT, que ele vai falar sobre nanotecnologia. Aqui, ó. A admirável mundo novo, a física e a tecnologia em escala do átomo. Então, também fica o convite. A atividade é bem informal. Quem nunca participou é bem gostoso. A cervejaria é um lugar muito bacana. E a gente tem uma terceira atividade voltada para o público geral, que é um clube do livro, que acontece online. Então, são encontros que acontecem a cada 2 meses, em que a gente convida cientistas para conversar sobre a literatura e a ciência a partir de uma obra. Então, o próximo livro vai ser com o professor Alberto, do CBPF, e ele vai falar sobre o livro que ele mesmo escreveu, que é a Mecânica Quântica para Jovens Sonhadores. O encontro vai ser dia 10 de dezembro. Fica aqui o convite, é muito legal também. O livro é muito gostoso, está disponível no site do CBPF para quem quiser baixar, então fica o convite aqui. A gente tem também atividades voltadas para professores de ensino médio, que acontecem online e presencial, em português e em espanhol. Então, se você é professor de ensino médio, fica aqui. Essa programação acontece ao longo do ano todo. E também, domingo, a gente tem uma sessão de ciência no cinema para crianças. Então, o programa de cinema cresceu e agora também a gente está fazendo programação infantil. O próximo filme é esse filme do Lightyear, que é da sequência do Toy Story, é a história do Buzz, é muito bonitinho. E quem vai conversar com a gente é o professor Ricardo Sturani, que é aqui do ICTP-Safer e do IFT também. Fica aqui o convite. Só que essa sessão acontece no Frei Caneca, que fica com o Cinema do Belas Artes, que fica no Shopping Frei Caneca, tá? Domingo, 13h. E se você também está aqui, a gente faz grandes reportagens apresentando áreas da física, e a última que a gente fez sobre ciências e tecnologias quânticas está no nosso site. Convido vocês a visitarem. Esse é o Ano Internacional das Ciências e Tecnologias Quânticas. A reportagem entrevistou 25 pesquisadores brasileiros, então fez um mapa geral bem extenso sobre a área no Brasil. Ficou uma reportagem muito bonita. Então, quem puder conhecer, é só visitar o site, está lá disponível. E aqui, as nossas redes sociais, para vocês acompanharem a programação. Aqui é um canal no WhatsApp em que a gente só publica os eventos. Então, quem quiser acompanhar pelo WhatsApp pode acompanhar. Não é um grupo, é só um canal mesmo, em que a gente anuncia os eventos para quem quiser participar. Então, agora, eu vou convidar o professor Jamir Marino, que é da Universidade do Estado de Nova York, para apresentar o professor Subir Sachdev, que vai ser nosso palestrante hoje. Muito obrigado, professor.
Obrigado. All right, so welcome everyone. It's a great honor for me to introduce Subir Sachdev from Harvard University. When you are faced with this task, maybe the basic question is asking the public who doesn't know who is our speaker today could just raise the hand, and probably nobody will do that. The way to summarize Subir's career is that basically he has been a theoretical physicist that has put together both truth and beauty in his research. So basically, on the side of truth, he has built concepts that are fundamental to all our understanding of quantum matter. So all spin liquids, spin glasses, all concepts of quasi-particles in modern language, they are mostly been started by Subir. And even in the last 5-10 years, he has kept contributing. Most of you are probably working or has worked on SYK models or have heard about it. So he's one of those people that kept pushing for his entire career. The side of beauty, Subir has the merit that basically has introduced to solid state concepts that typically are in field theory. So a lot of elegant language coming from large expansion parameters, transferring a normalization group in quantum context, they are again due to him. So his research path started 40 years ago with a PhD in 1985 from MIT. And he then basically, at the time, had an appointment at Bell Labs that were a very important thing in the US. He became professor at Yale. And I think in 2005, he moved back to Harvard, where he is still right now professor. Subir was so kind to fly early to Sao Paulo to give this public lecture. He will give more technical lectures on Monday and Tuesday. Everybody is welcome to attend. And because I basically mostly see young faces in the audience, perhaps in the spirit of the school, please interrupt him, engage him. Let's make this 7 p.m. talk active on Friday of Halloween night for everyone. So please, Subir, you have the floor. Thanks for coming to Sao Paulo.
Okay, mic is working all right? Well, thank you very much, Jamir. It was a very kind introduction, and I haven't heard quite that way presented before, so I'm very grateful. Very nice to hear all the two kind things you said about me. Yeah, so I'm also thank you for the invitation to be here. I'm very happy to be in Sao Paulo for the first time, although I've been in Brazil several times before. And also on Halloween night, I looked up, apparently Halloween is celebrated in Brazil, or okay, so thank you for, but I'll have a few connections to Halloween, as you can see in my talk. All right, watch out for the 2 spooky dreams. All right, so this talk is about the history of quantum mechanics and how it continues to evolve and really give us new insights into new things that have only been discovered a few years ago. So I'm going to give a very quick summary of the first 100 years, how quantum mechanics went from a theory of electrons in an atom, like hydrogen, to a theory of all kinds of complicated materials, and then turn to developments in this century, mostly, where we are still learning new things about quantum mechanics and its effect on large scales. So, all right. So the way quantum mechanics was discovered was really going from the large to the small. We had the theory of the Newtonian theory of the planets moving around the sun, and also the apple falling from the tree. So if you continue this to even shorter distances, you can ask, well, does it describe an electron moving around a proton in a hydrogen atom, which had already been discovered in the early part of the last century? And the answer to that was absolutely no. We need a whole different theory, which is what was discovered 100 years ago by Schrödinger and Heisenberg, called the quantum theory, and it gives a precise description of the motion of the electron around the proton, and says that it moves in certain orbitals that we are very familiar to in chemistry, and then those transitions between those orbitals explain how the atom can emit light. So in particular, if you take a gas of hydrogen and excite it, it emits lights at very specific wavelengths. And the theory of Schrödinger and Heisenberg precisely predicted all of these wavelengths, leaving no doubt in anybody's mind that was essentially the correct theory for one electron in a hydrogen atom. So we want to go not just consider one electron, one atom, but consider essentially an infinite number of electrons, say moving in a copper wire, and ask how does current flow in a copper wire. So copper, of course, it's a complicated atom, but there are certain electrons from the outer shell, which detach themselves from the atoms, and then move through the wire. So Sommerfeld already in 1927, just 2 years after the discovery of quantum mechanics, gave a theory of this, which is essentially the very basis of the theory that we study even today. And it was extremely successful. So the starting point of the theory is extremely simple-minded, and you would think it can't possibly work. You just think of the electrons as free particles moving through the wire, but obeying the laws of quantum mechanics. And you don't worry so much about the interaction between them, except for one very important fact. Just a year before, Fermi had introduced the idea of the exclusion principle, and certain particles, which includes the electrons and the proton, are what we call fermions. And a key property of a fermion is that no two fermion can occupy the same orbital or the same wavelength as these electrons are moving through the sample. So it's something very familiar in chemistry, where you just fill up orbitals to get the configuration of complicated atoms. So you just have to keep track of the Fermi exclusion principle and the fact that electrons are fermion, and that already explained some very puzzling properties of metals. And this basic idea is at the basis of all textbooks in solid-state physics, with some bells and whistles, up to, let's say, 1985. All right. So that extremely successful application of quantum mechanics to the large scale. All right. Okay, then actually before even Schrödinger and Heisenberg, there was another remarkable development. And this was by Bose and Einstein in 1924. They were thinking about light. Light as might be emitted by an oven or some other radiating body. And following the work of Planck, they introduced the idea that light itself is made up of particles that we call photons. And these, unlike electrons, do not obey the exclusion principle. You can put any number of photons in the same state. And once you allow this, they were able to explain many observed properties of black body radiation. Also, Einstein, in a paper slightly later, pointed out that if you imagine the bosons had mass, they were not light, but there were some bosonic particles with a definite mass, then they would all occupy the same state. And that will lead to what we now call a Bose-Einstein condensate, where you have large number of particles in the same quantum state. And today we understand to be the key to superfluidity and superconductivity, which I will say much more about now. And then finally, superconductivity is something that appears in metals. And the theory of that took a while to develop, but came out in 1957, where, again, they introduced the following idea, that pairs of electrons, which are fermions, but two fermions end up behaving like a boson, and they can then condense, as Bose and Einstein said, elementary bosons can condense. And this is, in fact, accepted today as the basic idea in the explanation for superconductivity. All right, so that's a quick summary of solid-state physics that you would learn in a graduate course up to 1985. I mean, these are the basic ideas. Of course, there's a lot of development beyond them, but this basic picture is essentially correct. Okay, so what's happened since 1985, let's say? Well, a whole new set of ideas have been introduced into our understanding of quantum mechanics on macroscopic scale. And the key idea is what we call quantum entanglement. And so new materials have been discovered, including these high-temperature superconductors. And there's a growing realization that you really have to think about a much more subtle property of quantum many-particle physics, not just the exclusion principles or the statistics of fermions and boson, but really a much more complicated way where quantum mechanics can combine when you have more than one particle. So that's what I'm going to try to give you a flavor of in the remaining part of my talk. So this has led to these studies of quantum materials have led to an understanding of the role of quantum entanglement on a macroscopic scale. And these ideas have also had an impact, in two-way impact, I would say, to many other fields of physics. So key ideas in quantum computing, quantum error correction, and somewhat surprisingly, even black hole physics have been interconnected to these developments on how quantum entanglement plays a fundamental role on macroscopic scales. And we really have to go beyond the ideas of Sommerfeld and Barty and Cooper-Schrieffer to understand so many materials and also many other systems. All right, so now let's get started. So let me tell you a little bit more about superconductors. Superconductivity was discovered in 1911, where Camerly-Onnes cooled mercury down to this very low temperature and found that it could carry current without any appreciable resistance. Okay, but you needed a whole room full of a refrigerator this big to create a little bit of a superconductor. But in 1987, there was the discovery of the cuprate superconductors. So here's a little piece of it. You can hold it in your hand. And it's a ceramic. The crystal structure is complicated, but I'll say a bit more about it in a minute. Don't need to worry about all the complications. But if you take a little piece of this and you dip it in liquid nitrogen, then you get a slab there, which is a superconducting material. So it can carry current without appreciable resistance. And one of the consequences is that if you put it over a track of magnets, it just floats. And that's because it so easily creates currents that can repel the magnetic field. And so that's, eventually, of course, it heats up. So when it gets above about 80 degrees Kelvin, then it's no longer a superconductor, and so it can't continue. So as long as you kept it cold, it would go forever. Okay, so of course now immediately the question is, can we use this for something? And there's been a big effort, international effort, to use these materials in all kinds of things, perhaps in electric power transmission. But in the last few years, I think the most exciting killer app, if you might say, of superconductivity is the idea that it could finally make fusion a viable source of energy, green energy. So what we have here, this is a cable made of YbCO, the yttrium barium copper oxide. That's the difficult part, making all these cables of the superconducting material, but that's now become an industrial process. And this will produce very strong magnetic fields, which will confine a plasma of deuterium hydrogen ions in here much more efficiently than conventional magnets. And maybe that will lead to fusion energy. So there's actually quite a few companies around the world that are using YbCO materials to make fusion machines, including this company in near Boston. So, and they have huge investors, and this could be the reason enough to study these materials better. Okay. Okay, so now let me say a bit more about these materials. What makes them superconduct at such a high temperature is not something we have a complete answer to, but I think we have some understanding. So it looks like a very complicated material, but you can simplify it and just consider one layer. And in each layer, you just have a square lattice of copper atoms. That's it, and you can forget about everything else. In fact, that gives you a very simple model of electrons moving on a square lattice rather than in free space. And furthermore, there's only one orbital of the copper that's important. So there's a certain material where it's not quite a superconductor yet. We have exactly one electron on each copper atom, and that's the material we're going to focus on. So this electron has a spin. The electron has a spin, and I'm going to just simplify it by putting an arrow. It can point either up or down. So it's spinning on its own axis. And what the electrons in the copper sites do is form this pattern. This is a pattern where half the electrons like the black squares on a chessboard are down, and the other half are up. So it's called an antiferromagnet. So this is what's observed when you take these materials at a certain density. And when you change the density, you get a high-temperature superconductor. That's the problem we need to understand. So already soon after the discovery, Phil Anderson and G. Bhaskaran made a very insightful suggestion, which we're still trying to work out in all its details. But the basic idea was that even though the spins are forming this very simple checkerboard structure, that once you dope it, then the spins do something very interesting. They form what you call a quantum spin liquid. All right, so what is that quantum spin liquid, or they all sometimes call a resonating valence bond state? Well, I'll describe it for you now. And we have a much better theory of it than there was no theory in 1988. Today we can say, after 30 plus years of hard work, we can really classify and understand at least the quantum spin liquid. All right, so what is a quantum spin liquid? Well, it has a key property that's entanglement. So now I have to explain what's entanglement. All right, so what is entanglement? Well, it's really something very simple. It's just the extension of a fundamental property of quantum mechanics called superposition to more than one particle. Okay, so you've presumably all seen this or heard about the famous double slit experiment, where an electron is coming through two slits, and it gives you an interference pattern very similar to waves when you average over many, many electrons. And quantum mechanically, we understand this by a very new concept that didn't exist in the Newtonian theory called superposition. We think of the electron as having two different states. One state is the left state, and the other state is the right state. And the actual state of the electron going through these slits is a superposition of those. You know, this is not something that Newton would have any concept of. You know, Newtonian mechanics, every particle has a definite position and momentum. Here, this particle, the electron, can both be in the left and the right sides. All right, well, that seems very counterintuitive, but that's the essential idea that was involved by Schrödinger and Heisenberg to understand the spectrum of hydrogen, and also the double slit experiment. So we just have to accept it, okay, that there will be superposition of states, and that's the key new idea in quantum mechanics. Okay, but what about superposition of more than one particle? So there was a brilliant paper by Einstein, Podolsky, and Rosen in 1935, where they pointed out that, quite skeptically, yeah, this is all very good, but once you get to more particles, there seems to be a contradiction. And what is the quote-unquote contradiction or paradox that they pointed out? So they said, okay, let's just take a hydrogen molecule, that has two electrons, and I'll highly simplify what's happening in hydrogen. I'll say there's one state of hydrogen where the left electron is up and the right electron is down. And there's the other state, which is this, with the opposite spins. And if you solve the Schrödinger equation for hydrogen molecule, you would, in some approximation, see that the actual state is really the sum of the two. Well, depending how you choose the signs, it could be the difference of the two also. That won't be important in what I'm going to talk about. All right, so you have two possible states of two electrons, and Schrödinger and Heisenberg tells you it's really in this rather strange-looking state where neither of them is up or not down, but they're always anti-correlated. So what EPR said, well, let's imagine a thought experiment where we separate these two electrons without disturbing their spin. Today, that's something we can do, but this was at that time just a thought experiment. And they said the quantum mechanics predicts, since you're not acting on the spin, that nothing will change. So this electron could be in this room, this could be, you know, in Boston, and if you did the experiment carefully enough, they would still be in the superposition state. So now you have this very strange non-local correlation between two particles that are causally disconnected from each other, although they were causally connected deep in the past before you separated them. And so now if I were to look at my electron here, and I see it's down, then quantum mechanics tells me that the other one should immediately be up. So there's some highly non-local effect here, or vice versa. If this was up, then the other one would be down. So this is what's sometimes called spooky action at a distance, appropriate for today. And I always wondered who called it spooky action for the first time. And the answer is actually Einstein did. In 1947, he wrote a letter to Max Born, and this is German, which I'm not going to try to pronounce, but I'm told that means spooky action at a distance. Right, so, you know, free from spooky action at a distance, those were his precise words in English, and that's how he described his own thought experiment. All right, today we know that does happen. There's nothing traveling between the two electrons, but the state of the electron is really not a local concept. So you're not really doing anything non-local, but you're dealing with a non-local object. But all the actions and information is all very local. Okay, so that's something we now understand quite well, and the experiment has really verified that you do have spooky action at a distance. All right, so that is the essence of entanglement of two electrons. So how about entanglement of more than two electrons? Well, strangely enough, the basic ideas of more complicated entanglement go back to 1865, well before the discovery of quantum mechanics. And this was discovered by a chemist called Kekulé, and he actually did have a spooky dream. As you can check on Wikipedia. He said he discovered the ring shape of benzene. He was thinking about the benzene molecule after having a reverie or a daydream of a snake eating its own tail. All right, so what did Kekulé say? Well, chemists knew about bonds between electrons, and in benzene there are 3 bonds between 6 electrons. So one way to make the bonds is this way, and another way to make the bond is the other way. Today, we know from quantum mechanics that each bond is exactly this EPR pair that I've told you about in the hydrogen molecule. So now, which one is it? That was the puzzle. And the trouble is that if it was either one of these, then benzene, consisting of 6 carbon atoms, would not be a perfect hexagon. This bond would shorten, and maybe that one would be longer. You get a rather ugly-looking shape, which is not an hexagon. So is it this or is it that? And Kekulé said, well, it's both. They resonate. So today we know that we would say that it's a superposition. It's an entangled state of 6 electrons. Yes? Sorry?
I lost the part when you said it's not an hexagon exactly.
Well, suppose, you know, chemists just draw bonds. Before Kekulé, chemists would just draw a bond. So suppose this was the configuration. Now, so this bond is different from that bond. So the energy of this is different than that, and so it'll naturally become smaller or bigger. There's no reason for this length to equal that length because their chemical structure is different. So it will no longer be a perfect hexagon. Yes? Sorry, what? Intersection of bonds? No, you can't do that. I mean, I think chemists had already understood that each electron can only form 1 bond. It can't do 2 bonds. So the way you superpose, so this is, in the model language, the way you do it is all 3 bonds have to move. You can't have 2 bonds at the same time. That was part of the rules of chemistry, and that's something also part of the rules of quantum entanglement, it turns out. Yeah. Sometimes called the monogamy of entanglement. So each electron has to pick a partner in any given configuration of the wave function. But they can be a superposition of 2 different configurations. Okay? They can partner in 2 different ways, but they have to choose a partner in each component. Okay? Good. All right, so Now that you understand, that's great, you understand Kekule's idea and how it connects to quantum entanglement, we are ready to understand spin liquids. So the place where spin liquids were originally introduced by Anderson and Fazekas was on the triangular lattice. Now this is not on the YBCO material, you have a square lattice, but there are other materials, like this particular material here, which does have a triangular lattice of spins. In this case, they sit on the ytterbium atom. So one configuration of the spins is a kind of a simple configuration, similar to the antiferromagnet on the square lattice, where the spins just point in some definite orientation, and in fact, in many such materials, this is what they do. But way back in 1975, was it, 74, Anderson and Fazekas postulated there could be another state. And here the idea is very similar to Kekule. So the spins locally, they want to form a bond with another spin. So here's a bond, which is this state here that I've been talking about over and over again, just this entangled pair of two spins. So now you have a whole lattice. You just don't have a hexagon. You have an infinite lattice. And you have to form bonds between nearest neighbors. So here's one way to do it. And you can think of this as what we call a dimer covering of the lattice. There are these dimers here, which are the ellipses, and there can be only one ellipse on each site. So this is one possible dimer covering. All right, so similarly on the hexagon, there were two dimer coverings. Here, there's really a huge number. If the lattice has 10 to the 23 electrons, the number is e to the 10 to the 23. There's an exponentially large number of such coverings, and I just show you some of them. These are all valid coverings. There's a huge number of them. And so Fazekas and Anderson postulated that perhaps, just like Kekule did, the ground state, the actual low energy state of the system, is a superposition of all of these. So now this is a huge step. Where in benzene you just had entanglement of 6 electrons with 2 dimers configurations, you have a macroscopically large number of such configurations. So this would be a state with, today we'd say, a long-range quantum entanglement. It has massive entanglement. It's macroscopic with a superposition of lots of different configurations. Okay, so this was just a very short paper of 2 or 3 pages pointing this out, and nobody worried about this from 1974 till about 1988, when the high TC materials were discovered. And that's when we started developing a theory of what these states are like and what are their observable consequences. Entanglement sounds very fancy with all these configurations, but it's hard to detect. If you did an experiment and looked at the system, you would just see one of these. And you wouldn't know that all the others were there in this actual wave function, because every time you looked at it, you would collapse it if you wish. You would only just see one of them. So how could you tell that there is this entanglement, even if it's there? And that's been one of the, the hard questions that we now have very good answers to over lots of theoretical and experimental work. And in fact, one of the key properties of this macroscopic superposition of dimer configurations is this. That is, any such macroscopic entangled state has excitations that cannot be created by local operators. That is, it has some excited state, some high energy state, which you cannot create on its own. There's nothing you can do to just create one of it. And so this new excitation is now called an enneon because it doesn't behave like a boson or a fermion in general, and that's the funny name that people have come up with it. So let me give you a simple example. So say you had this entangled state, and you came in and you kicked one bond, so you kicked that bond, and so these spins, instead of being locked into a singlet, this APR pair, just say they become parallel to each other because you locally perturb them. All right, so that's an excitation you can create locally just by hitting it on one site, but that's not the actual excitation the system wants to be in. What can now happen is that one of these can move right off to infinity, And now you have this lone excitation, which we call a spin-on. It's just a single unpaired spin moving around. And that's the anion. And the thing about this object now is that there's nothing you can do locally to remove it. It has a certain rigidity. It's doesn't, anything you do is going to change the number of spins, free spins, by mod 2. So as long as you count spins by mod 2, then the evenness or the oddness is completely preserved in the quantum state. And that's really one of the most fundamental way of thinking about these states. It's this long-range entanglement that gives you these local states that cannot be created by local observables.
When you're saying longer range entanglement, you mean that the correlations decay algebraically in space? No.
Well, okay, I'm being very, they may or may not.
Okay, maybe I can bring the
I would define long-range entanglement in the other way. The definition of a long-range entanglement is precisely that it has anions. Like this. That there are excitations that cannot be created by a local operator.
Okay.
To me, that's essentially equivalent to long-range entanglement.
Okay, so the adjective long range should be actually the adjective non-locally removable or something like this, because it always confuses me when people say this is long range entanglement as opposed to what? To short range entanglement? And then I start to think.
So it is true that if you had, if I drew some valence bonds that were not resonating all over the entire system, then that system would not have anions. That's just but you could not create. Anything you created can be created by a local operator because there's only short-range resonation bomb. So long-range quantum entanglement is a loose word. I don't know, I haven't defined it. So let me define it. I'm defining it this way.
But your coverings cannot go very far away. So like you are limited by next neighbors when you do these pairings with.
Well, no, you can put any short-range pairing you want. I'm talking about really an infinite sample, so it doesn't matter. You could have anything short-range or even decaying with a power law, that's usually enough. But
you cannot have an EPR pair built between this guy and a guy that is very far away from it.
You could do that, but that's exactly what quantum computers want to do. That's very hard to do, but yes, you could do that in principle. Yeah, so that's one anion. That leads me precisely. There's another type of anion where it's much more subtle. You remember, you take these states and you superpose them, infinite number of them. There are these numbers, C1, C2, C3, C4, C5. I haven't told you what they are. Well, that's what you need the theory for. So we understand something about their structure. And then you can create an excitation where you sort of create a branch cut. And every time a dimer crosses the branch cut, you pick up a minus sign. So this is another excitation, sometimes called a Wison. It's a very subtle change in the ground state, but it's once you created it, you can't get rid of it. And you can only create them in pairs, just like the spin-on. And so this is the other excitation that's present in the very simplest quantum spin liquid. So I'm going to now jump right ahead to today. So it was understood already in the early 90s exactly how to understand this simplest state. And there was a beautiful solvable model called the toric code by Kitaev in '97. And Kitaev also made a very insightful observation that once you have this incredible stability of these anions, if you could hide your quantum information, just like you said, by making an EPR pair of anions, then that quantum information, the fact that it's an EPR pair, cannot be disturbed by any local operation. So that's roughly the idea between quantum error correction, that when you superpose anions in complicated states, that is robust to local perturbation because local perturbation don't change the anionic nature. And that's the idea behind also the Google quantum AI experiment on a bunch of superconducting qubits to create, in this case, only a single logical qubit, which is protected from all kinds of errors. Okay. All right. So Now move on to the, getting back to superconductivity. So what we have seen is that the theory of spin liquids came out of thinking about superconductors, but it's had an impact somewhere else. Its most dramatic impact has precisely been on the problem of quantum error correction and perhaps using it in quantum computers. So that theory has really gone much farther than there was anything that was available in 1988. And now all these amazing experiments are being done in very different systems to test the ideas. Okay, but what about high temperature superconductivity? Well, it turns out the kind of spin liquid you need to understand high temperature superconductivity, I think people are now accepting, is something very different than the one with well-defined anyons. So there's a toy model, of course my favorite model, which gives you a somewhat different type of entanglement. Now the important thing now is that you notice now in everything I was talking about, the electrons themselves were not moving. There were some very subtle correlations between their spins and their valence bonds, but each electron was stationary. It wasn't going anywhere. It was just orienting its spin in some very complicated ways. But in a superconductor, the electrons actually move. So we have to understand how you get entanglement with moving electrons, which are fermions. And so the SYK model turns out to be a simple model that allows you to understand that in a very simple configuration. So here's the second dream, which I just made it up. But following Kekule, I had to bring snakes into it. So this is the ancient Indian game of snakes and ladders, where you move along, and every time a snake bites you, you go down. If you have a ladder, you go up. Anyway, the basic idea, there are snakes. Think of each snake as entanglement between all kinds of random places. And that's really all the SYK model is. So here's what you do. You take a bunch of positions in which fermions, like electrons, can live. And so some fraction of them are occupied by fermions. And now you're going to entangle them in the following manner. You're going to allow these electrons to tunnel, as we say, to move around in the lowest energy state so that you get some complicated entangled state. But you're going to only allow them to move in pairs. So for example, the electron on site 11 and 12 can move to sites 5 and 14. Now in quantum mechanics, anytime anything that happens that's associated with the complex number, this is the complex number here, which is called the amplitude. So there's an amplitude whose square is the probability for a certain process to happen. So this is one such process, but there's many others. So each such process of moving a pair of electrons has a certain amplitude. So to give you the Schrodinger equation, to even write down the Schrodinger equation for this system, I have to give you a table with all these amplitudes, all these complex numbers. So if you have order n electrons, it's of order n to the 4 complex numbers I have to give you. Okay, so then you say, what's the problem? I have these numbers. Why not just solve Schrodinger's equation? Unfortunately, that's easier said than done, because the Schrodinger equation lives now in a huge space. It lives in a space of 2 to the n possible configuration of the electrons, just like the dimers also had exponentially large number of configurations. And it's just impossible to solve. We can't solve it. The best computers in the world could not do it beyond about 30 electrons. And even that's quite tricky. So what we realized in 92, 93, was that for a closely related model, that you could solve this with one assumption in the limit of very large numbers of particles. The assumption was that these numbers are random numbers. They have no particular correlation with each other. That's all. And that would be true, for any set of numbers with probability 1, really. So with that assumption, we could solve this. We couldn't quite write down a wave function, but we could say something about how various excitations would move around. And what we found was something quite remarkable. We found that in this very simple model, you get some complicated entangled state. then you can naturally ask, just like I asked about the spin liquid, what are the excitations of this state? If you perturb it, what moves around? In the other state, we had spin-ons and this other complicated Wison. And what are their statistics? Well, here the answer is there is nothing. There are no particle-like excitations, no bosons, fermions, anyons. So if you created it, you wouldn't see any particle-like object sitting there. So it's some very much more complicated type of entanglement that doesn't permit any kind of particle-like excitations. So if you put this on some large system and you want to flow some current, because these things are moving around, well, this is the best I can say. There's some entangled mess. You'll create some lump that's going to move around and dissipate away, and that's going to carry the current. Okay, so that sounds very abstract, but there's one thing we discovered, along with, I should also put George and Parcolet here as key ingredients. Sorry, I forgot that. Key contributors. So this is my only equation here in this talk. Turns out this system obeys something today called universal Planckian dissipation. So here, you take the system and you kick it a little bit, and you watch the energy relax away, and you ask, how long does it take before everything settles down and the system is heated up a little bit? That gives you a time tau. And then you ask, what is this time tau? Well, it turns out the time tau, if you do it slowly at frequency 0, is just this very simple number, h bar, Planck's constant, divided by Boltzmann constant and the absolute temperature. In particular, the values of all these u's doesn't matter at all. And that's quite shocking when you go back to how simple metals behave in Sommerfeld's theory. In Sommerfeld's theory, the relaxation of the electrons is controlled by the strength of the interaction between them. That's what happens when you apply the Boltzmann equation. Here, it seems the Boltzmann equation doesn't apply at all. And you get this universal Planckian behavior, and also at finite frequency. Okay. So this was actually quite exciting to us when it was discovered, I think around 2000 or late by Parcolet and George. And why was that? Well, because in the high temperature superconductors, so now I'm actually showing you the full phase diagram, there is this region called the strange metal above the highest DC. And everyone now agrees that understanding the strange metal is really a precursor to understanding why this DC is so high. This is some density away from the antiferromagnet. So what people had already done, and now has been done much more precisely, is people measured this relaxation time in this strange metal. And what they found was this relaxation time, this is a more recent experiment, and I'll talk much more about this in my lectures on Monday and Tuesday, that this time, again, is of order h bar over Planck's constant. So, of course, now I'm not going to say that we should take this toy model, this toy SYK model, excuse me, and use it to describe strange metal. But that's the question we've been thinking about a lot. And there's an extension of this SYK model in 2 dimensions, which I also will say more about next week, which is described in this paper a few years back, which in fact has exactly this property. So it's an extension which cures all the artifacts of the toy model, but doesn't throw out the key property, which is the Planckian dissipation that comes quite naturally in this calculation. All right, so that's really all I'll say about it. Okay, so finally, in the remaining few minutes, am I done? No. Yes.
Maybe actually a couple of questions. So, being Planckian relaxation and
yes.
Not having quasi-particles is a if and only if. So as soon as I have one, I imply the other, and vice versa. Or there are cases in which I have Planckian relaxation in systems that have quasi-particles, or they are not strictly strange metals.
I think they usually go along. I'm trying to think of any exception. Nothing comes to mind, but I don't know of any proof. Yeah. Yeah.
And so you are saying in this phase diagram, there is SYK physics somewhere? Because strange metal is not synonym of SYK physics, right?
Well, okay, so this is what I'll talk about next week. Maybe not quite the appropriate discussion here. But there's an extension of an SYK model that you know
Answer
about.
that question.
Yeah, which has finite dimensionality and all of that. So it gets rid of some undesirable properties of the SYK model, like the zero temperature entropy, but it doesn't get rid of the blank anticipation, which is why we were very excited and wrote this paper a few years back.
And strange metal, this means just metal without quasiparticles here. It's
well, it
metallic
means
behavior.
much more. It means that, for example, you have the Planckian relaxation, you have the linear temperature resistivity, you have T-log T-specific heat, you have some T-squared Hall effect that's going to appear next week in a paper. So there's a whole host of properties of this particular strange metal that this model does give correctly.
Okay.
Okay. Sorry for that side talk for the experts, really. But now let me just say a few words about what was, a complete surprise to me. But it turned out that this toy model that we've been playing with way back in 92, 93 is also now a key ingredient in advancing our knowledge of the structure of black holes when you apply quantum mechanics to them. So I have about 5 minutes, so I can say this, okay? Yeah, it's not going to get very complicated. There are, of course, experts on this question. So what is a black hole? Well, a black hole is a solution of Einstein's gravity theory, which appears when the mass of the black hole is compressed to a very small volume. And in fact, a radius smaller than the Schwarzschild radius, which is twice, this is Newton's constant g, the mass of whatever the object is, divided by the velocity of light squared. So if you took m to be the Earth's mass, this radius is the size of a pea. So you'd have to squeeze the Earth to the size of a pea, and then it'll become a black hole. That's how dense it is. And then what happens that once it's so dense, light cannot ever escape from the inside of a black hole or anything. And so in the Einstein's theory, the center of the inside of a black hole is forever lost to you. It has no connection to the outside because nothing can ever come out. Okay, that's the classical description of a black hole. And although the idea already goes back to Schwarzschild in 1916, it wasn't until in this decade really that a lot of evidence has been accumulating for the existence of black holes everywhere, including at the center of our galaxy. These are huge black holes with millions of solar masses associated with them. Okay, but Hawking and Bekenstein in the late 70s started thinking about, purely as a theoretical exercise, quantum effects near black holes. And a simple way to understand what their ideas were was to you just take my favorite EPR pair of an entangled pair of electrons, and now you separate them, but you put one inside a black hole and one outside. And now since the horizon is actually nothing special, nothing happens to a black hole falling into the horizon. It's only when you go to the very center, an electron falling into it doesn't even know it's fallen through the horizon. It's only when you hit the very center, which we assume will happen later, but before it hits the center, and then there's no change to the entanglement between these two particles. They're still entangled. Okay, so this particular idea, in a different form, was what led to Bekenstein and Hawking to actually give you a result for what we call the entropy of a black hole. So the basic idea is that you have some observer outside, and the observer, say, sees 1/2 of an EPR pair, and that observer has no knowledge of this other pair. And so to that observer, this electron is just a random bit. It can be either up or down, because there's no way you can access the information on the other side. So randomness is entropy, as we learned from Boltzmann. And therefore, roughly speaking, there is entropy associated with black hole, because there are always these entangled pairs on the surface of a black hole. And so this type of analysis led Hawking to actually give you a precise formula for the entropy of a black hole, and it's proportional to the area of the surface because it's associated with these entanglement of EPR pairs. At least that's the picture people draw. Okay, what we know today that this is not quite correct. Entanglement is not so simple. But a better picture would be a whole bunch of SYK models on the surface of a black hole. It's complex entanglement. It's not just a simple two-particle entanglement. It's complex long-range entanglement of a certain type. And the reason I can even say this is turns out to be for certain charged black holes at low energy, a precise correspondence between the equations of entanglement of this black hole and Einstein quantization of Einstein's equations. All right, so that's something that has come out of a lot of work in the last, I guess, almost 20 years now. No, 10 years, sorry. That there's an intimate connection between this picture here and the kind of entanglement you would deduce from extending Hawking's theory to understand better the nature of entanglement around a black hole horizon. Okay, that's really all I'm going to say about it. So let me conclude this part of the talk. Oh, one more thing I want to say. So this sounds very mysterious, but there's another thing that actually gave me a hint as to why there might be this connection. In 2010, I wrote a paper pointing out there was a connection. And this is the following fact. You could ask, what is the relaxation time of a black hole? What does that mean? Well, suppose you have two black holes, and they're spiraling in. We should have a movie here, but eventually the black holes would merge and form a single black hole. So you can ask, how long does it take for these two black holes to come to rest in a single sphere? So that's what's called the ring down time. And it turns out to be Planckian, where T is Hawking's temperature. So this was a fact known to many people in black hole physics. And it was one of the facts when I learned about it, I said, that reminds me of the SYK model. And that has turned out to be much more correct than I dreamed when I first came up with this proposal. All right, great. So to conclude this part of the talk, so in the first part I talked about this spin-liquid entanglement that leads to anyons and quantum error correction and maybe quantum computing. Now we have a more complex type of entanglement with moving electrons, moving fermions, and it leads to some complicated types of many particle states in which there are no anyons or any other particles. Particles just kind of lost in this quantum soup. And these ideas are turning out to be helpful, in particular understanding various aspects of the high temperature superconductors, which I will say much more about next week. And amazingly, have also been in a different formulation, something called duality. It's also leading to new insights into the evaporation and the interior of charged black holes. So, thank you.
So the questions can be in Portuguese if you want. The idea is just have the questions be as basic as possible. Don't try to be technical. Good.
Pode ser. Não, acho que. I have a question about the entropy equation that you showed us. It only gives us a hint about the lack of information that we have about the entanglement, right? But I cannot think about how does it say something about the entanglement itself? Because when I think about the Hawking radiation and all that stuff,
Yeah.
for me it's quite clear, okay? But I can understand how does it connect with the entanglement itself. You know what I mean?
Well, you know, I think as became clear also from some questions by Jamir, I mean, entanglement is it's a rather imprecise word. It's something, you know, what is entanglement? Well, entanglement is anything that cannot be described by thinking of the electrons obeying one electron Schrodinger equation. That's my definition, okay? So it's a very broad definition. And I think we are long ways from making a table, okay, this is one entanglement, there's another entanglement, that's another. This is the different classification of entanglements, and these are all distinct from each other. And how you would even measure it, I mean, it's not something easy to measure. Okay, so we're long ways from all of that. But what I've described are two classes of states, those of the well-defined anyons, and those which have this kind of Planckian dissipation, where we can really compute almost anything you want, including entanglement, entropy, and so on. You know, yeah, so I don't know, what maybe you can make a question. That's the best I can do. So here, of course, I talked about the entropy, but this entropy is not so easy to measure.
Yeah.
What you measure, and this is, you know, what you measure is the Hawking radiation in principle, although that's never been measured, but it's easier to measure in principle.
I think
and,
the main concern of
so this is just, you know, at this point, what I presented are some very rough ideas, and interpret them in terms of this entropy because it's intuitive to us. But these ideas are also, you know, in the end, you don't really use all those words. You have actual equations. You have these equations that you can write down for the dynamics of these electrons in this quantum soup. And they turn out to be deep connections, the equations of Einstein and Maxwell, which was a complete surprise, but they do.
Okay. I kind of understand it. I just think that the cern of my question is that when we talk about the Hawking radiation and the entropy itself, it's quite clear that we're talking about multiple bodies and that stuff. But we start from a dual concept, and it's kind of strange, I think.
Okay, I won't disagree with that. You're right, it's kind of strange. It wasn't obvious at all. It's just, you know, but through the efforts of many, many people, this remarkable structure has now come together, which has so many things that work so well that I don't think there's any doubt that it's correct. Yeah, but if you want to give me a non-strange, simple explanation in a few lines, I'm sorry, I can't. I've done the best I can.
Okay. Thank you.
Good night. I think it's kind of a simple question for an ungrad student, but I'm kind of thinking, like, because it has so many visual things, I'm kind of trying to imagine if it's right that, like, for a superposition, it can be very far away, like infinity far away, one particle from the other one?
Yes.
Like infinity. It can be, like, tangled, but it's like infinity large.
Well, I mean, if you were in a perfect vacuum, of course, it could be infinity, but, you know, that's, you know, if you wanted to do the EPR experiment, where let's take the simplest case of just two particles. As I said, the key word there was you don't disturb the spin. So that means as you were separating these particles, here we go, as you were separating these particles, if you encountered even the slightest perturbation to the spin, you would lose the entanglement, okay? So there's always some dephasing at some length scale. So in fact, this experiment is done with light, because light is, instead of spin of electron, you do polarization of light. And that is very well preserved. Light goes through light without feeling each other.
Okay, like really ideal space for it to...
No, you do it in optical fibers or in free space.
Okay.
Light interacts very weakly, and so you can really make entangled photons over or kilometers these days.
Okay, kind of crazy, because like...
Yeah, but no one's done that with electrons.
Okay.
But this is a key obstacle to making good quantum computers, is to have this entanglement over really big distances with something other than light.
Yeah, thank you very much.
So in the SYK model, of course, again, this is a model, and in the ground state, there is true entanglement, but nothing's ever at 0 temperature. There's always some temperature. And so the consequence of this infinite range entanglement is precisely this Planckian dissipation. You then find that the way temperature gives you some decoherence in the entanglement is kind of universal, and it's just given by Planck's constant over temperature. That's something that's come out of a lot of theory.
So like not as simple as
yeah,
thinking
so
of
that
ideal, but
yeah,
it is really far. It can be.
Well, I
really
mean,
far.
I don't know of a simple way to explain it,
Yeah.
but if you know a little bit of quantum field theory, then it's possible to talk about it, but I don't know how to do it without that. Yeah, but it's a good question. And it wasn't obvious at all, otherwise, years ago.
So I don't know if this is a too disconnected question,
Yeah.
but from what you said last about the connection from your work to black holes, I was imagining that you would say something like the ER equals EPR conjecture about entanglement being described as a wormhole, and
Yeah.
from
Okay,
particles.
well, I didn't go into that. Of course, I just limited myself to the entropy of black holes, because that's something I understand a little better than
Yeah,
ER equals EPR. But it is a very much an extension of these ideas, that the entanglement is actually quite a bit more complicated. And when you take this entanglement and extend it over larger distances, you can get wormholes. But yeah.
How exactly?
I think Nathan would be a better person to tell you more about it.
Yeah, but again, I don't know if you can answer that, but how exactly would the description be of creating a wormhole inside a black hole, which would be like, some kind of crazy distortion of space-time or something like that?
Yeah, well, I think you need some very bizarre forms of matter for the wormhole to form. To get a traversable wormhole, that's something Maldacena and Chi and others and Jeffreys have talked about. Yeah, I don't think anyone has any idea how to do that. But one thing I just heard from Juan Maldacena just a few weeks ago, because I'm no means an expert on this, but he was saying that even if you made a wormhole, a traversable wormhole, you would not go through it in faster than light or instantaneously go from here to the thousands of galaxies away. You would not do that, at least from the point of view of the outside observer.
Yeah.
But the person going in the wormhole wouldn't age, but the people outside would see that it would not be a faster than light effect. So that part of the wormhole Star Trek story is not quite correct.
Okay, thanks.
So maybe I try to, let's say, not be technical and stay at the level of the colloquium. So let's start with the original example, superconductors, right? So
Yeah.
you told us about Cooper pairs, they behave like bosons.
Right.
And when you have 10 to the 24 particles, like Avogadro number, the equations that describe superconductivity are classical equations. We can write them in a line and solve them with basic knowledge of partial differential equations. And same story for SYK, right? You are talking about massive entanglement that is in the model, but as you actually have proved, in the large limit of many particles, you can write down a relatively simple classical equation and still solve the problem. So do you know a phenomenon in which massive entanglement prohibits you to write or to simulate the problem with a few classical equations, or still in a manner that is technically bounded? Is the question clear? It's confusing, right?
Let me try to, I'm not going to rephrase the question. I'm going to answer the question that I think I should have, that I want to answer. And then you can come back.
Yes.
So the way I'm going to answer is the following.
I understand it being convoluted, yes.
So if you start here, this blue region, then the Sommerfeld theory works perfectly fine here, okay, where the electrons are just almost independent of each other. So the Bardeen-Cooper-Schrieffer really was telling us how do you go from Sommerfeld to superconductor, where then all these electrons, which are all independent of each other, start to just form pairs, and the pairs will all sit in the same state. And that theory works over here. Okay, as far as it would be what I would write down. I would write down exactly the same classical theory of BCS, and I would have a description here. But what is the theory that takes me from this extended SYK strange metal to the same superconductor? That's largely an open problem. We don't have a full description of that. That is the problem now, is to understand how we go from this complicated entangled metal to a high temperature superconductor, you know. And another phenomenological fact is that every material that has a high TC has a strange metal above it. So it's very tempting to say, well, there's a causal effect. Somehow this entangled mess will give you a high TC superconductor. And I think that is the heart of the problem we still have to solve. You know, what BCS succeeded in doing to Sommerfeld's theory, we have not yet succeeded in doing to the theory of the strange metal. That is the problem we're working on.
Actually, you answered a more interesting question than the one I wanted to ask, so I'm very happy.
That was my purpose.
Very happy.
Thank you, Professor, for the nice talk. What do you think about the hypothesis that in the high TC superconductors, for example, in the skew plates, the antiferromagnetic fluctuations acts like a glue of the Cooper pairs instead of the phonons in the BCS theory?
Well, I would give the same answer I just gave. I think that's correct, and it's correct over here. What's going on here? Well, the antiferromagnetism gives rise to something we call the pseudogap, and in fact, that pseudogap has some spin-liquid aspects. So exactly, the question then becomes, how does a quantum spin-liquid become a superconductor? Yeah, so that's a different theory, which I don't know, maybe I'll have time to talk. That's what we've been writing papers on the last couple of years, and also for the strange metal. But I think that is the correct description. It's the correct description over here, though. And it's probably the correct description everywhere in many other superconductors, like the pnictides, like the electron-doped superconductor cuprates. Maybe less so for the nickelates. We don't know yet. There's some interesting many-body physics that seems to be present in the nickelates, too. But that picture, which is successful in helium-3, for example, where you have some exchange of spin fluctuation, give you pairing instead of phonons. Very successful theory, and it seems to apply in many, many places, except in the most interesting place, which is the place with the highest TC. That's why I think you have to go beyond that theory.
First of all, thank you very much for the talk. It was very pleasant. My question is, I don't work in condensed matter physics. I work in another topic, but I remember a while ago there was a lot of noise about room temperature superconductors that turned out to not be true or something along those lines. Could you talk a little bit about what is your view or what is the community view on whether room temperature superconductors are possible, or will we have them eventually?
Well, I'm certainly hoping we will. Okay, first of all the recent noise was about a very different class of materials, which I have not discussed at all, under very high pressure. These are very tiny samples in huge pressure, so that makes them very difficult to measure anything easily. I mean, these are pressures comparable to the pressures at the center of the Earth. So these are very highly compressed systems. And I think there was a claim you could, in some not so high pressure, you could do it at room temperature, and I think that's fallen by the wayside. But I think there is, there's now more and more evidence, even of something at 180 Kelvin. Okay, room temperature 300 Kelvin. But anyway, so that's the highest TC we have of any confirmed TC, it seems. But also, again, at very high pressure. Okay, so that's one side. And there, it's basically the BCS theory, but of phonons, of lattice vibrations. Because you have hydrogen, phonons have rather high frequency, and that seems to be the reason you can get such much higher TC than the old BCS superconductors. I mean, these materials, you know, what's very striking about them is that, as we just heard, the important part is the antiferromagnetic exchange interaction. So what's special about the cuprates is the magnitude of the strength of that, the coupling J, that gives rise to this antiferromagnetism and also superconductivity. That coupling is about 101,600 Kelvin. Okay, so that's well above room temperature. So why does a coupling of which is 1,600 Kelvin give you a TC of only 80 Kelvin? Maybe you would tweak a little thing, it would go from 80 to room temperature. 300 Kelvin is still well below J. So that gives me hope. Somehow, some magical chemistry can raise this to room temperature. I mean, I think we don't know. But I will say that, you know, liquid nitrogen is very cheap. You don't need liquid. That's not the biggest problem with these materials. If I want to make, you know, a fusion energy or high distance power transmission with these superconductors, I think the temperature is not the main bottleneck. Exactly. Thank you very much. What is the bottleneck? Well, first of all, for long-distance power transmission, it's simply, there's already very good infrastructure. You've got to replace everything with little cables with liquid nitrogen, and you just got to put a few refrigerators along the way. It's not that expensive. But there's a startup cost. And here, it's not so much you cooling it. That's not really the problem. It's that there's all these you know, neutrinos and other particles coming out here, and they damage the material. So you just got to make it a much better, it's an engineering problem, making the material very solid and resistance to some of the radiation coming out of the fusion. So there's all these engineering issues. I don't think temperature is the big one.
I see. Thank you very much.
Yeah.
Any other questions? Okay, so let's thank Subir again for a wonderful lecture. So again, Monday and Tuesday, he'll be also lecturing if people want to hear more. And coffee and juice upstairs if people want.